Yesterday, any question from yesterday? First, no. Yeah. Just give it a moment. Great. Yeah. So yesterday we saw here, okay, on the how we find the number of activated complex, intermediate, as well as the delta H of reaction. Okay. So today we'll be looking at how the catalyst can affect the rate of reaction. Okay. So you can first turn over to this page of the note first. So it should be. Oh, I think I printed like in the wrong way. Okay, so there are two identical pages here. Sorry. So yeah, there are two identical pages. Okay, never mind. So you can maybe take out your notebook and write this down first. Okay, so the Maxwell-Boltzmann distribution. So we discussed this curve yesterday. So no need to spell this word. Okay, so Maxwell-Boltzmann distribution. We can use this curve to explain the effect of temperature and catalyst on rate. Okay, so that's what we are going to discuss today first. So we can use this distribution to explain the effect of two factors on rate. So number one is temperature and thank you. Okay, so the effect of temperature and the effect of catalyst on rate. So first, let's begin with the effect of temperature. So how does temperature affect average kinetic energy? It increases. Okay, so that's the first thing we want you all to put down. So the effect of temperature. So you can jot down these points first. Increasing temperature will increase the average kinetic energy of particles. Okay, so and that will have two effects. So this would increase the proportion of molecules with kinetic energy greater than or equal to EA. It will also increase the frequency of collision. So remember, don't say number of collision. We say frequency of collision because we need to factor in also time. Okay, factor in also time. So frequency of collision means you don't just look at the number. You look at how many times of collision happens in a certain period of time. So increasing average kinetic energy will have an increase in both of these factors, which ultimately will lead to an increase in rate. And we are going to explain this using the curve we described yesterday. So remember how increasing temperature will affect the curve. We already saw how increasing temperature will affect the average KD, right? But how does it affect the curve from yesterday? So let's draw two graphs in here. A blue line represents a lower temperature, let's say 298 Kelvin. A red line represents a high temperature, 308 Kelvin, let's just say. And on the notebook, I want you to sketch this Maxwell-Boltzmann distribution. What are the axis labels for the y and the x-axis respectively in the Maxwell-Boltzmann distribution? The number or proportion of particles with that kinetic energy. X-axis is kinetic energy. Okay, so x-axis is just kinetic energy. So I'll copy this graph for use later. Yeah, just copy the axis label first. Can you draw what the Maxwell-Boltzmann distribution curve is like for 298 and 308 Kelvin? First of all, is it a normal distribution, Maxwell-Boltzmann distribution? No, it's asymmetric. And the peak, should it be closer to the left or to the right? For the 298 Kelvin, it should be closer to the left, like that. Okay, so if you can draw this curve in here. What about the red one? What happens at higher temperature? So at high temperature, what will happen to the peak? Would it be taller or lower? Lower. Would it be found further to the left or to the right? To the right. But you should try to draw it in such a way so that the area under curve remain unchanged. Because what does area under curve represent again? The total number of molecules. Okay, so you see I tried to draw it in such a way so that the area seems to be the same. Okay. Of course, we're not going to integrate to check if they're the same. But make sure you draw it like this. Don't draw something like this. Don't draw it like this. Apparently they have different area. And the examiner, when he sees that, when he or she sees that, it will immediately take away your point. Make sure you draw it in such a way so that the area appears to be similar. So just put down what you need to be careful of. Number one is that the peak, okay, should be lower and further to the right. So write this down, the peak. So this is the peak. Should be lower and further to the right. So further to the right hand side. Because what is that point that we can draw on this graph right next to the peak? That represents the average kinetic energy, right? Remember? So this is the average kinetic energy at 298 Kelvin. So average KD at 298 Kelvin. So where's the average KD at 308 Kelvin then? Yeah, somewhere here. Remember, the average KD is always to the right of the peak because of some complex math. So just know that it's not right where the peak is, but somewhere to the right. And then what? We can now use this curve to explain why increasing temperature will increase the rate. First, do you remember the energy requirement? How much energy must the reactant have before they can react? They must be greater than or equal to activation energy, right? So activation energy appears as a straight line, a vertical line on the Maxwell-Boltzmann distribution. So you can put the EA here. It's a straight line on this graph. Anything on the left, do they have enough KE or do they have enough KE to react? Anything on the left will not have enough KE to react. So you can maybe take a look at this line here. The x-axis represents energy. So anything to the left of the EA bar means that the KE is less than the activation energy. And anything with KE greater than EA will be able to react. Can you compare the area now? Compare the area under curve for the blue curve. And compare this to that of the red curve. Which one has a larger area? The red area or the blue area? The red one. And because the area corresponds to the number of molecules, it means what this graph is showing is that at 308 Kelvin, the number of molecules that have KE greater than or equal to EA is larger than that at 298. Do you get the graphical meaning? Having a larger area means, having a larger red area means there are more molecules at 308 Kelvin than at 298 Kelvin that can meet this requirement. Okay? And we can also draw another graph on here that shows 318 Kelvin. Okay? And it will be even more obvious. You see the relationship. If you like, you can draw a third one here. Can you see that the yellow area is in turn larger than either of these, right? So that means as you keep raising the temperature to a higher and higher temperature, the area on the graph for where Ke is greater than or equal to EA, it increases. It becomes larger. Okay, so put down the conclusion below, please. Okay, so the conclusion that you can draw from this graph is that as temperature increases, the area on the graph, which represents number of molecules, okay, so the area on the curve, which represents the number of molecules, where Ke greater than or equal to EA increases. So therefore, this together with the other factor, you know when things move faster, they bump into one another more rapidly, right? When things move faster, particles bump into one another more rapidly. So this is why these two terms, they are parallel each other. They are not consequential of one another. It's not like this will lead to that, but at the same time, both of these factors are caused by an increase in Ke. Okay, so together, they will lead to an increase in rate. Okay, so at the same time, so you can say at the same time, as temperature increases, the frequency of collision increases. So these are two parallel factors. Okay, so frequency of collision increases. So it is because of these 2 points that the rate of reaction increases. Okay, so together they explain why the rate increases at higher temperature. So if you ask me which is a more important factor, this one is a more important factor. So this is the major factor. This factor below is a minor factor. It's not as important. Okay? What is important is that the area grows like noticeably larger when you raise the temperature. So that's what you can learn from the Maxwell-Boltzmann distribution. Any question about how we interpret the Maxwell-Boltzmann distribution first? The effect of temperature. Because now we're going to use it in a different way to explain the effect of catalyst. Okay? So now on the right hand side, I wanted to draw the same graph again. But this time we show the effect of catalyst. So effect of catalyst. So catalyst, if you remember, it is a chemical that speeds up the reaction by providing an alternative pathway with a lower activation energy. So this time, what we are doing is we'll keep the curve unchanged. Yeah, remember the curve will be different when temperature changes. So it means when you are studying the effect of catalyst, you don't change the curve. So can you put down what is changed and what is not changed when we study the effect of temperature? So put this here. We change the curve. We keep the EA unchanged. You see, I only have positioned a single EA value here. I did not change the EA to something else because what we are studying the effect of temperature. So we can only change temperature by changing the curve. And so here you can see temperature or the curve is changed, but the EA is fixed. Now on the right is opposite that, okay? So we have the curve to be fixed, but the EA is changed, okay? Because that's what a catalyst will do, right? So a catalyst will lower the EA, so you can write down EA is changed, but the curve is fixed. So EA, so that's what you need to pay attention to when you draw the graph. So EA is changed, curve is, EA is changed, but the curve is fixed. Okay? So therefore we have only one single curve below, but we are moving the EA. So can you now draw two EA? So this is the EA, before we add a catalyst. So we call this EA uncatalyzed. Uncatalyzed means the catalyst hasn't been added yet. So does the catalyst lower or raise the kinetic, the activation energy? Lower. So the new EA should be drawn to its left. So can you draw it that way? Okay, so this is EA catalyzed. Okay? Now, do you know what I'm going to do? Is to find the area under curve again. So first, we need to find the area under curve with the OEA. So the OEA is this one. The area is only this thing. What about the new area? The new area will be this one. Okay, when you use the catalyst, you see the area is noticeably larger than before, right? Can you see that? Yeah, so this is why they are both explained using the Maxwell-Boltzmann distribution, but we are changing different things at different times. So read the question carefully. When they ask you what's the effect of temperature, you keep this purple line unchanged. You are shifting the curve. It is as if you're pulling on this curve. You are making the peak appear taller or make the peak appear shorter. So this will affect this part of the area. But when you add a catalyst, you are lowering the EA. So the EA becomes a lower value. And this will also have an effect on the area. It grows bigger. So in other words, the area will become bigger under two conditions. Number one is when the temperature is increased. Number two is when the catalyst is added. Is that clear? Yes? Okay, yeah, so put this up, okay. First of all, you can write addition of a catalyst. What does it do? It will provide, let's try not to say lower the activation energy. Instead, say it provides an alternative pathway with a lower activation energy. Yeah, you can choose not to write activation energy in full. You can just write EA. Both are uppercase letters, just that this A is a subscript, okay? And what will happen? Yeah, so the new EA will be lower. So the EA catalyzed will be lower than the EA uncatalyzed. So what effect does this have on the area? Well, this would increase the size of the area you see, and therefore resulting in an increase in rate. So I want you to review this using this flow chart. Okay, later when you do revision. Okay, so it's through this flow chart that you can explain the connection between temperature and rate, and the addition of catalyst and rate. Yeah, so in exam they will ask you how does temperature affect rate? So of course these are not shown to you. You have to remember this and write this as the answer. And they may ask you how does addition of catalyst affect rate? Well, first you say it will increase rate, and what happens in between is these things happening. Okay, so write down this conclusion below. So the conclusion here is that as a catalyst is added, as you can see in the above diagram, so as a catalyst is added, the EA catalyzed will become lower than the EA uncatalyzed. Draw also the energy profile we described yesterday to support this. Remember, the EA catalyzed will always be lower than the EA uncatalyzed. So this is the catalyzed path. And on the left, you have the reactant. And on the right, you have the product. So you can see that the EA catalyzed, these two, they are both shorter than the EA uncatalyzed, right? Is that clear? Yes? So this is EA uncatalyzed. So also, don't mix up Maxwell-Boltzmann distribution and energy profile. What do we call this graph on top? This is called the Maxwell-Boltzmann distribution. Just look at the y and the x-axis. They have different labels. What about this one? This one below, we don't call this Maxwell-Boltzmann distribution. We call this the energy profile. Yeah, so when they ask you to draw the energy profile and Maxwell-Boltzmann distribution, they're two different curves. Don't think they're the same thing, okay? So this is the energy profile, aka energy level diagram. Okay? What are the y and the x-axis again? So we described the y-axis yesterday, but I think I forgot to tell you what the x-axis is, and I'm adding it there now. what was the y-axis of this graph from yesterday? Energy. And the x-axis is what we call the reaction coordinate. It is the direction in which the reaction happens. You know, reaction always called reactant to product, right? This is why we have reactant on the left, products on the right. It doesn't mean time. Yeah, it means something similar to time, but it's certainly not time. Because if this were time, it means the reaction mixture will spend this amount of time as the reactant, this amount of time as the activated complex and the intermediate, and this amount of time as the product. You know, that's not what it means, right? It's just telling you that reactants will eventually become product. That's the meaning of right now reaction coordinate. So I want you to remember these labels for me then. Okay, yeah, take out a highlighter. Proportion of molecule of that Ke, and this is Ke, energy, and reaction coordinate. So each of these axes labeled here, they are specific to a certain type of graph. Okay, so let's finish this conclusion first. As we add a catalyst, the EA catalyst is now lowered. So the area under curve, for like a catalyzed reaction is greater, is larger than that of the uncatalyzed reaction. So there is an increased proportion of molecule with Ke greater than or equal to EA. So there is now a greater proportion of molecules with Ke greater than or equal to EA. Therefore, there is more effective collision. And finally, we have an increase in rate. Yeah, so this is what they expect you to write in exam when they ask you, state the effect of catalyst on rates. So they are giving you this first term and this last term, and they have you figure out the rest. Write out these in the exam. Okay? Yeah, I have a very interesting analogy to share with you so you can understand it more easily. You can think of, remember the analogy I used yesterday, right? This is like the percent of students with that score. This is like the score, right? So if you think of having a reaction means passing a test. How can I increase the passing rate of the test? Well, there are two ways. Okay, is to have the student work harder. So you see, this factor here is kind of like asking the student to work harder by shifting the performance to the right, to a higher score, right? This is the first thing, I can increase the passing rate. What is the second way to increase the passing rate? Is to lower the passing score. Think of EA as like a passing score. So you see, I have the same curve here, right? I'm not changing the curve, meaning I'm not changing the student performance. However, what I can do is I can lower the passing rate. So let's say originally I said 80 points or 80 marks is the passing score. So only this amount of students pass the test. But with the same student performance, I can now lower the EA to a lower passing score. Let's say 40. 40 guarantees a pass. Do you see that with the same curve, I can get a larger proportion of molecule. Okay, so this I think is a very useful analogy, which I want to share with you. And maybe you can use that to understand what is happening. So the analogy is that reaction is analogous to passing a test. Okay, so passing a test. So what is the EA analogous to? EA is analogous to the passing score. So KE is analogous to the student score. Okay. And temperature is proportional to the performance, for example. Okay. So maybe this will help. That's what I wanted to know in here. And then we're not done, unfortunately, with the rate equation. So now I want you all to turn to this page. Yeah, I'm sorry about this print here, because if you check, there are actually two identical pages here. Doesn't matter. What I put on the last page actually is this thing. So if you have jot this down on your notebook, it's fine. So now we'll turn to some math-intensive calculation next. I hope you have your calculator ready. Okay. So we'll now look at the last bit of rate equation Yeah, it's called the Arrhenius equation. Do you remember that the rate equation has 3 different components? What are the 3 key components? The rate constant, K, what else? Concentration, what else? What do you call those power? Order of reaction. Yes, okay, I'm not going to take into detail because we have mentioned this quite a few times already. So recall that it links rate to 3 factors. Okay, so one is the rate constant, the other is the concentration, and finally order of reaction. Okay, so order. So we can summarize it this way. We have rate equals K, concentration term, raised to a power, like that. Okay, so you have A, B, M, and N. Now we look at another equation. So another equation is the Arrhenius equation you see in here. It looks even more complicated. But don't worry, the questions are really simple. Okay, about this equation. Okay. Okay, so you can maybe sit at the back. So this is the Arrhenius equation. So if you take a look at that equation on the notes right now, it says K is equal to AE negative EA over RT. So you may recognize some of these variables, okay, or constant in the equation. So this is the same K you just saw, the rate constant K. And then we have a few new terms in here, such as Arrhenius constant. I'm not sure if you can see it on the back. So this is Arrhenius constant. So it has a fixed value, just like other constant you observe, like pi, and like among other things, or maybe R. R is also a constant. So R is another new constant called the universal gas constant. So the value will be given to you in the exam, so you don't have to memorize that. And I'll show you how to use it and how to use the calculator to find that. And of course, we have also EA on top. So this is the same activation energy we just saw. So activation energy. And last but certainly not least, we have Kelvin temperature. Okay, so this is in Kelvin. Don't use the Celsius temperature. How do we convert between Celsius and Kelvin temperature again? Plus 273 to degrees C Celsius temperature. Okay, so write down this conversion if you don't already know. So degrees C plus 273 gives you Kelvin temperature. For instance, 25 degrees C translates to 298 Kelvin. So we plug that into this equation. But actually, we seldom use this equation in its negative form, in this form. So if you ask me what does this equation really show, it shows the relation between K and T. And it's more like an exponential relationship. So can you draw this? So we have, well actually this line is going to draw this graph. So we can draw this on there. So you have K, label the y-axis as K, and label the x-axis as Kelvin temperature. So this is Kelvin temperature. The graphical relationship looks like this. It's an exponential increase. So when you increase the temperature, K will not increase linearly, but it increases exponentially. Okay, so this is the cause, and this is the effect. Okay, so in layman terms, it means the rate constant is larger when temperature increases. That's it. That's all the Arrhenius equation does. So we say the higher the Kelvin temperature, so the higher the Kelvin temperature, the larger the rate constant. But because the rate constant is tied to the rate equation, you can see that when you increase the rate constant, you will also increase rate. So this is another cause and effect. I want you to put down. So you have cause and effect. Yeah, so when you do revision, maybe put some numbers here so you see the connection. So number one is that you are increasing the temperature in here, then the effect is that the value of rate constant will increase. And then point number 3 here is that when the rate constant increases, then point number 4, the rate will increase. Okay, so you can put down this logical flow on the right. as temperature increases, K increases. And as K increases, rate will increase at the end. So this is the consequence of rate equation and Arrhenius equation. So now we'll look at a more useful form of Arrhenius equation, because like I said, we seldom use Arrhenius equation in its negative form. So we will log it, okay, sometimes even learn it, okay, but in this you will just log it for I don't know what reason. So here you can put down K is equal to AE negative EA over RT. I want to remind you all of a few log rules that you have learned in math. I don't know how to explain this rule to you anyway, so you can maybe put down this log rule. When you have log AB, what does this simplify to?
Log A plus log B.
Yes, log A plus log B. And when you have something like this, like log, like m to the power of n, what can this be simplified as?
N times log n.
Yeah, n times log m. So you need to be very good at using these log rules here, at least in this part. Okay, so let's do this. We are logging both sides now. Okay, so you can treat this as one term, this n as the other term. Okay, so we are applying the first rule here, and we are applying the second rule here. So let's do this. We have log k equals to log a plus log e to the power of negative dA over RT. So we can now apply the second rule onto the second term. You can move this power over to the front, like we did in here. You see you're basically just moving this n to the front here. So what this expression will become is, so you can see that we are moving this over. So we are moving this term over. Okay, so we will now have negative EA over RT times log E. And if you type this on your calculator, so if you type this on your calculator, so log E will give you something like this. Yeah, just a weird number. Okay, but then we will reciprocate it. Okay, we will do 1 over that. And then you will see that this expression simplifies into a more useful form, which is negative EA over RT times 1 over 2.30, like you see. Yeah, if this all looks very scary, don't worry, we are getting to the end, we are seeing the light at the end of the tunnel. This can be converted into the linear equation form that you will really be using. It's log K equals to negative EA over R times 1 over 2.3 times 1 over T, and finally just one more time, just bear with me, plus log A. So this equation may not mean anything to you yet, but trust me, it looks like what you have learned in math class. It's y equals mx plus c. So what is the shape of this? What is the shape of this?
Straight line.
Yeah, it's a straight line. Okay, so if this all looks very scary, don't worry, the nightmare is over. Okay, so you can put this
What's your straight line?
in this space. Okay, it's log K equals negative D over R times 1 over 2.3 times 1 over T plus log K. Now what we are going to do is we will plot this as the y-axis and this as the x-axis. So in exam they will give you a bunch of K value and T value, but be careful, you must not use these directly. You need to turn these K and T value into log K and 1 over T before you can use them in the in this equation. So, and I'm sure all of you can do this. If you are given some K values, how are you going to convert it to log K? Well, just log it, right? So you can put down, you log these numbers, and then you will be able to get the log K values. And when you have T, well, they will give you the T in degrees Celsius, sometimes, okay, to trick you further. So first, write down the steps. So first, how do you convert degree C to Kelvin again? To 7, add 273 to that, okay? So convert degree C to Kelvin by adding 273 degrees to that. That's the first thing you need to do. The second thing you need to do is to reciprocate it, meaning you take 1 over. Okay, so take the reciprocal of t. Allow me to give you an example. Like if for some reason they why don't we use the values in here? Okay, so you see at the bottom of the page there are some data that we can use. If they give you a field, this time the question is a little bit easy because they are giving you temperature in Kelvin already. So let me convert that back to degree C first. So we have 362 degrees C, let's just say. And they are giving you the rate constant to be 1.995 times 10 to the power of -8. What you need to do is to log the K value by typing this on the calculator. So you type this on the calculator. So 10 to the power -8 times 1.995. And then you log it. And then you see -7.7 down at the bottom. So that's how you get -7.7 there. So that should be the easy part. The second part is you need to convert this to Kelvin first. So you type 362 on the calculator, you add 273 to that to find the Kelvin temperature, and then you reciprocate it. Okay, 1 over. So 1 over that. So, and this is the number you see, 1.57. Yeah, I know you'll be surprised because this number appears to be a different one that you have on the calculator. Because do you notice on the column label here, it says times 10 to the power -3. Times 10 to the power -3. So that means the number 0.00157 can be written as 1.57 times 10 to the power -3. And this scaling factor will also be plotted on your x-axis. Okay, so now, just like you learned in math, a graph, a Cartesian coordinate system has the x-axis and the y-axis. But because most of the log K value here are negative, so we are only showing this quadrant of the Cartesian coordinate system. So just this quadrant, so we are showing this part here. So can you draw the graph in here? So we have 1 over t, the x-axis, and we have log K in here. Yeah, I know you will be really confused because normally when we draw a graph, we draw a graph looking like this, right? Yes, but why are we showing the graph like this now? That's because the log K value, they are negative. Can you see that in here? Yeah, so these log K values, they are all negative. So we are only showing this quadrant of the Cartesian coordinate system. Yeah, of course, if you insist, you can also complete the rest of the diagram. But most of the data point, I tell you, they fall on this part of the graph. So therefore, when you actually plot those values, like for example, the first one is 1.57 times 10 to the power -3 and -7.7, you get a dot here. And when you plot the other data point, you get the other dots. So what remains, okay, is for you to find the slope. How do we find slope? We find the change in y, we divide by the change in x, so we do the rise over run. Okay, so this is rise is dy, run is dx. So the slope, or the gradient, will be equal to change in y over change in x. But note that this is a negative slope, because it points this way. So positive slope look like this, negative slope look like this, so this should have a negative value. So you can do negative in here, you can put a negative in here. Okay? So, and for this diagram here, you will have to use a ruler to actually find, to actually draw a triangle here first, and then find 2 points, okay, to find the change in y and the change in x value in order to find the slope. So, for example, in here, let me move this over. So, why don't we take these 2 points? You see 1, 2, 3, 4, 4 points on your graph, right? So let's take the first point and the last point here to demonstrate what we need to do. So this is 1.15 times 10 to the power -3, and what is it, -6. You can put down these coordinates first, right on the graph. The second coordinate we will be using is this one. So for example, this is 1 point, 1.45 times 10 to the power negative 3, and the y value is negative 7.3. So yeah, can anyone tell me what is the rise value? What is the rise value here? How do we calculate the rise value? You know this is x comma y, the xy coordinate of these 2 points. So how can I use these two sets of coordinates to find the rise? Which two number can I subtract?
Negative 7.3.
Yeah, 6 and 7.3. I only take the difference here, the magnitude, because I know that the slope would come out negative anyway. So if you like, you can ignore the sign for now. Just make sure that at the end you add a negative sign in here. You can just use the magnitude. Just use the number part. Ignore the sign in here, because if you also take into account the sign, it will make it very, very complicated. Okay, so just do 7.3 minus 6. Okay, so we take the magnitude only, and then we always remember to put a negative sign here. And what about the dx? It would just be, oh, this is 1.115. Yeah, excuse my typo. Okay, so this is 1.15. And this is 1.45. So should I do 1.45 minus 1.15 or the other way around? Yeah, just always get the larger number and subtract the smaller number from it. Okay, because at the end we know that the answer will be negative. Okay, so if you do this, you will make less mistake. Okay, so 1.45 times 10 to the power negative 3 minus 1.15 times 10 to the power negative 3. And to add to the complication of this question, you need to look at the unit as well. What is the unit of 1 over T? First of all, what is the unit of Kelvin temperature? K. So 1 over T would be per Kelvin then. Okay, so write down the unit here. Because temperature has the unit Kelvin, 1 over T will have the unit Kelvin to the power of negative 1. So when you log a number, do you remember the unit of rate constant? Is it fixed or is it variable? Depending on how you write the rate equation. Do you remember in here we have, where did we mention the rate equation here? So this is when we discuss the rate equation. K has a unit of per second for this set of data, right? Then in another set of data, K has the unit dm cubed per mole per second. So this is to say the unit of K is variable, right? Yeah. But don't worry, when you log the number, you take away the unit. This is the same reason why when you find the pH from concentration, do you all remember this equation?
Yeah.
Concentration, of course, has the unit.
Mole per dm cubed.
Mole per dm cubed. But when you find pH, because you have used log in the process, you take away the unit. So this is why pH has no unit. Okay, same thing here. Yeah, I know I just asked you what unit K has. What unit K has, it doesn't matter, because at the end when you log it, it has no unit. Okay, so write down why. So taking log removes the unit. So taking log removes the unit. So now, if they were to take the question out a notch, and they ask you what would the unit be with what would the unit be with your answer? Okay, so you can write, because change in y has no unit, and when you divide by change in x, which has a unit per Kelvin, what is the unit of slope then?
Kelvin.
Kelvin, yeah, so the unit will be Kelvin. Okay, so we'll see what we can do about it, but can you first type this on the calculator, because it's very inconvenient for me to type it on my calculator without trying. So this is 0.3, okay, but anyway, I figured it out. So 3 times 10 to the power negative 4, and this is 1.3. So make sure you also verify this on your calculator. So we have 10 to the power negative 4 times 3. So this is the denominator, so I need to flip it, times 1.3. So do you all get this number? Yes. Okay, so negative 4333 Kelvin. But this is not the answer we are looking for. Why? The answer we are looking for is hidden in the slope. Can you see that the activation energy is part of the slope, right? It's not the slope itself, but it is part of the slope. Now, all that we need to do is to make EA the subject. Okay, so let me copy this equation to the next page, just before. So we have this thing here. So we have this equation. You remember that slope is equal to m and is equal to this very complicated term. Okay, but don't worry, it will become clear, okay, very soon what this value is for EA. We just saw that the value of the slope is negative 4333 Kelvin. So now we just have to make EA the subject. Okay, so this is now math. This is not chemistry anymore, but just math. Can you help me make EA the subject? Well, first of all, we can take away the negative sign because it's on both sides. Can you make EA the subject?
Yeah.
Just make EA the subject.
Yeah.
I'll give you 30 seconds. Just make EA the subject. Show all the other stuff on the other side. We'll check the answer in 30 seconds. And you should also type the numbers on your calculator and to find the numerical value. R, by the way, is 8.314, or just 8.31. And it has the unit joule per mole per Kelvin. So let's just check the expression for EA, for finding EA first. So EA is equal to any answer. What should be on the other side? I just need the expression. No need for the number yet. So it's 4333. Oh, that's 2.3. Sorry, this is 2.3. Yeah, times out times 2.3. Yeah, 2.3. Okay. So remember where the number 230 came from, right? It's from. I lost track. Okay, don't worry. Okay, it came from log E and then 1 over that. Okay, so you have E when you log it and then you reciprocate. This is the number, 2.3. Okay, it's not 230 but 2.3, the same number. So when you type this onto your calculator, 4333 Kelvin times R. R has the unit joule per mole per Kelvin. Okay, and then you multiply by 2.30. Can you tell me what will be your final unit? Joule per mole, because the Kelvin and the per Kelvin part, they got cancelled out. So the Kelvin and per Kelvin, they got cancelled out. Leaving behind joule per mole. So yeah, if you really don't care about the unit, it's okay. Just remember that at the end, you need to, what do you need to do to convert this back to kilojoule per mole? Divide by 1,000. Yeah. So if you really don't care about the unit in the intermediate stage, it's fine. Yeah, but I try to explain to you how the unit comes to be kilojoule per mole here. So finally, let's just type everything onto the calculator. So we have 2.3. We can just use this rounded number, as this is the number you will use anyway, times 8.31 or 8.314 times 4333. So this should be 82,816 joule per mole. When you divide it by 1,000 and round it off to 368, you get 82.8 kilojoule per mole. And what do you notice? EA, does it come out as a positive or negative number? It's always a positive number. So can you put down a very important point on the side? So note, EA always comes out as a positive number, because what's the definition of activation energy? It's the minimum amount of energy needed to start a reaction, right? Do you remember?
Yes.
So it's the minimum amount of energy needed to start a reaction. So because you need to put in energy to break bonds, yeah, energy must be required. Okay, this is why it has to be positive. Remember, positive energy change means is it endothermic or exothermic? Positive. Endo. Endo means energy is absorbed. So if they ever ask you why would EA be positive, that's because it must be endothermic. So it must be endothermic, as energy has to be absorbed to break bonds in order to start reaction. So to break some bonds, to start a reaction. Okay? Okay, so now, let me share with you another method for finding EA, which they will probably also ask you. The first method I listed here is the graphical method, where you are required to plot a graph. The second method requires only the calculator. Okay, it's called the 2-point form. Okay, so you can look at this side of your plot right now. So we have the graphical method on the so the graphical method is this one. The simultaneous linear equation method is the one that I will show you now. So like in this question, so what is given to you? So you have two different temperature in Kelvin already, so they are saving you the trouble of converting it into Kelvin yourself. And then you have rate constant, so I'll just put K in here. Yeah, don't mind the unit. I know it's set mole per diameter per second, but you don't need it anyway, as you will log it anyway, okay, at the end. So the unit doesn't really matter here. So you have two sets of values, 673, 773, and 8.38 times 10 to the power negative 4, and 7.665 times 10 to the power negative 2. Can you check out a highlighter? If you have two different colors, even better. Okay, so help me convert temperature into the respective 1/T first. Yeah, if you have, I think you have enough space. Can you create two columns? One column to the left of temperature, and you call it 1/T. You need to do 1 over these numbers to obtain these values. Okay, so, and now take out your calculator, find me the reciprocal of these two numbers. So you basically have to do 1 over 673 and 1 over 773 and show me the answer here. So you have this number. And for the K column, can you create yet another column to its right? And you call it log K. And this time you need to just log it. So the mathematical manipulation is different. One you do reciprocate. One you do log. Okay, they're different. So I'll do it alongside you. So you have 673, 1 over that. Remember to store the number on your calculator, or you will lose accuracy. Okay, so you have 1.49 times 10 to the power negative 3. And when you do 1 over 773, you all know how to store the number, right? No. But I haven't used that calculator for quite some time. I think it's shift store, and then there's a letter, like shift store A, shift store B.
Oh.
Yeah, you can try it, okay? But you can use the history function on the calculator for now. So 1 over 773 will be 1.29 times 10 to the power negative 3. And for log K, yeah, I'll wait till you give me the answer. Okay, so all of you work on this quietly, individually first. Type this number on your calculator and log it. I want to check if you know how to use a calculator. Okay, so yes. Convince me, okay, that you know how to use the calculator. So we'll check the answer. Okay. Do you get the same number?
Yep.
As this one? Yeah. Negative 3.08. Again, you should use this number, store it, okay? And then you have 7.65 times 10 to the power negative 2. And then you log it. You should get negative 1.12. So store it, okay? So what you need to do now is to plug this number into two equations. Well, actually into the same equations. And, yeah, so plug these numbers into the two equations. So we have the first set of data. Yeah, so you can now write log K. What is the log K value of, I'm sorry, I think I flipped the colors around. So this should be green and this should be yellow. Okay, that. Okay, so let me just fix this real quick. I don't want you to be confused later when you do revision. So give me a moment. You have log K, negative 3.08 and negative 1.12. So this should be in yellow, and this should be in green. So let me take away these two things first. Okay.
You want
So
to
we
buy
have
the bag.
so we have 1 over t and we have learn k. Right. Okay. So now let's plug the numbers in. Okay. So for the first one, we will do negative 3.08 is equal to negative dA over r times 1 over 2.3 times 1.49 times 10 to the power negative 3. Yeah, and trust me, this is just math. This is not chemistry. Okay, this is math. This chemistry is math. Yes. Since the beginning. Okay.
What?
Yeah. Okay. Yeah.
We're not
So-
at the end yet.
Okay, yeah, don't worry. I'm sure you can do this. Okay, I'm sure you can do this. Okay, so let's just call this equation 1.
Okay.
Yeah, so this is equation 1. Can you do the same for equation 2? Can you plug those numbers in and form another equation? Yeah.
Oh no.
And then you know you will have to solve for a dA. Okay, so yeah, so I think all you can do this. So negative 1.12 equals negative over r times 1 over 2.3 times 1.29 times 10 to the power negative 3, and then plus log a. You know why I never talk about log a? Because it doesn't matter. It will be gone anyway when you subtract the two equations. So yeah, let's do this. It's up to you. You can do 1 minus 2 or equation 2 minus 1. It really doesn't matter. Okay? So which do you prefer? 2 minus 1. Okay, so let's do 2 minus 1 then. So 2 minus 1. Yeah. Yes?
We can't find out A also.
You don't have to find a.
No, but if we use the simultaneous, we can just find both EA.
Yeah. You can eventually find a, but it has not much use at this level. Yeah, you can of course find also a, but it's not important. Okay? So what is 2 minus 1? So you have negative 1.12 minus, be careful, just like in the Hess's law chapter, sign is important. If you forgot to copy a sign, you're screwed. Okay? So therefore, make sure you type also the bracket on your calculator just to play safe. Okay? So when you subtract these two equations, you take this number, you subtract that number from that. And then you have negative dA over r. Because this is a common term, we take it out. And then we just subtract the green terms. So we have this number minus this number. So minus this number. And log a is gone. Remember, log a doesn't matter, right? Because when you subtract 1 from 2 or 2 from 1, this whole term will just like go away. It doesn't concern you. So now, what you need to do is to type this on the calculator. So make dA the subject. Yeah, I know both methods are hard, but they both are rooted in math. Okay, so you need to just keep it to yourself. EA cannot be negative. If you get a negative number, I'm sorry. You need to check.
I'm just starting over.
Yeah, you need to check your answer. EA must come out a positive number. Yeah, so yeah.
197.
Well,
135.
actually, I don't know the answer. Let me just check it as well.
Oh, I don't know.
So for those of you who already know the answer, keep it to yourself first.
I can't. Attack.
So this would be, yeah.
A basic math.
If you think you will make mistake, it's better to just calculate each chunk first. Don't type everything on the calculator. Okay? Don't put all eggs in one basket. Okay?
Yes,
So you
sir.
type just this part on the calculator first. You have negative 0.20 times 10 to the power negative 3. And then you can deal with these smaller parts. That will be easier. So you have 1.96 times 8.31 times 2.3. So this will be this number. And then you multiply this by, so times 0.2. Yeah, and then you multiply it by this number.
Bruh.
Okay. Yeah, and so wait a second.
This
So
is
negative 2.
It's not even chemistry anymore.
Intensive math.
Yeah, it's literally intensive
8.31.
math. It's basic math.
So negative 2 minus
Yeah,
1.
just simultaneous. Get up.
Right,
Out. This
so
is simultaneous.
2 minus 1.
Can we use
Yeah, this
one?
M2 even like you can't even like see this in M2. It's too easy for
So
you.
you have 1.96 on your left. So 1.96 times 8.31 times 2.3 divided by
Lost. Like
this number.
M2, right?
So do you all get this one?
Simultaneous thing.
No one is doing.
Can anyone get this answer?
No, I'm lost. I don't know what's happening anymore.
Oh, you know what's
Sir, you're
happening?
wrong.
Okay, step by step. Okay, let me copy this onto the next page. Yeah, this is why for this question you must not rush. Because if you rush, I can guarantee you that you'll get it wrong.
Hey, I'm not divided.
Okay, so let me break it down for you first. Do you all get 1.96 here first? Yes, okay, so maybe now you can just move,
That's positive.
yeah, you can just move this term on the left first. Can you just treat this as a yellow term and this as a green term and tell me what should DA be if you need to express it in terms of yellow and green term?
Green times
So DA is equal to yellow term times out times 2.3, then
Oh, divide by green.
divide by green, yes. So maybe because you like a mix up, okay, the order. So this is why you get it wrong. Now try this again.
I want to try.
Put 1.96 here and put negative 0.2. Well, you can forget about the negative sign now because the two negative sign I have already brought it up. Okay, yes. Yes. Okay. We have to make sure.
No, you're wrong. You're wrong. I'm right. You're so stressed. You need to go.
Okay, right. So
Yeah.
let's
Even
just
I
try
use
this.
that method. I still got this.
So 8.31 is the value of out. So can you all try this again?
Huh?
Out is 8.31.
187.
No.
Yes. If you get
What's
that,
that?
that's the same number on my calculator. This one, right?
Wait.
Yeah.
8.31.
And to make sure that everybody is out.
Divide by what?
0.2 times 10 to the power negative 3, which means 2 times 10 to the power negative 4. If you can't type this on the calculator, is 2 times 10 to the power negative 4.
Negative 3 minus 1.2.
Let's go.
9, right? So
Do you get that number? This same number. It has to be the same. It can't just be
yeah, I
close.
got that as well.
Yes, okay. So what is the unit that comes straight out of the equation? Is joule per mole, right? But very often they will ask you to convert that to kilojoule per mole. So what is it? Divide by 1,000. Okay, so what is that number? You don't need a calculator for this step. You just move the decimal point. So we move the decimal point 1, 2, 3 steps. So we have 187.
197.
197 you got. Oh, let me try this
Sorry,
again.
what can you scroll? Is that 4.44?
Which one is 4.44?
1.44.
1.96.
This is 1.96.
No, the green one.
The green one is 2
No,
times
up
10
one,
to the
up,
power
up,
negative
up,
4.
up.
1.49.
1.29, 1.49.
Yeah, so 1.49, 1.29 give a difference of 0.2, right?
Yes.
Yeah.
1.49.
Yes?
I mean, I got the same answer.
This is 2 times 10 to the power negative 4.
That's 2.
Because 0.2 times 10 to the power negative 3 means 2 times 10 to the power negative 4.
Oh.
Okay, let me show you. 0.2 times 10 to the power negative 3 means 2 times 10 to the power negative 1 times 10 to the power negative 3, right?
Yeah.
And then now we are using index law. 10 to the power of negative 1 times 10 to the power negative 3 means 10 to the power negative 1 plus negative 3. Yeah, so
Can I quit chemistry?
you also get this answer.
I thought we were doing chemistry. Why are we doing math?
Well, part of chemistry is math.
How much of chemistry?
What, 90% of chemistry?
No. That's why I pass.
Well, this is why you need to type the number carefully.
That's
what
why I
I'm doing.
pass.
Okay, that's what I'm doing. Do you all get 187 kilograms of paper?
No.
And
Yes.
then
Close.
How about the university?
they have many steps.
University chem, I think you just.
But I thought the math you do in DSC is harder than this.
No.
No?
No. Easier. You want to see our DSC
But
paper?
this is just
This one
multiplication.
easier.
What have we done? Just multiplication and division.
Plus and minus.
Maybe section B.
Okay.
Section
Okay.
So, like,
Yes.
is that like always like the second equation minus the first one? Can
Oh,
we
you can
just
also
do
do
the
equation
first
one
minus
minus
second?
two.
If I do the first one minus the 2-1, it's like
Well-
197.
Oh, let me tell you why is it okay to do either. Because if you do 1 minus 2, this part will become negative.
Yeah.
There's no escape. There will always be a negative number,
Yeah, yeah.
either in the yellow term or the green term. So do you see what we just did?
Yep.
When we do 2 minus 1, I have, like, avoided getting a negative number here. But I still can't avoid getting a negative number in this part, you see? This is negative, right? There's no escape. If you do 1 minus 2, 1 minus 2, this will become
Get
negative.
the
And this will be positive.
opposite answer.
If
No,
you
this
do 2
is
minus
197,
1,
not
this will be negative and this will be positive. There will always be a negative number somewhere.
Right.
So don't think that you can take one part and not have a negative number. That's not an option. Okay? You need to overcome your fear for these numbers. Okay? Yeah. So but don't worry. Yeah, usually this only make up a very small part of it. I don't want just this small part to ruin your experience. Okay? With
Already.
Too late.
Okay, don't worry. Then let's not put all eggs in one basket. We look at other parts of this chapter. There are also other parts that stresses, explanation more than calculation. Yeah, I know the calculation here is complicated. There's no denying.
So can
all that.
you could just pause it there. I want to check it again.
What?
Keep it there. She wants to check it.
Okay.
Please.
Oh my
Oh, she will
god.
post.
Yeah, I'll post on Google Classroom.
Move on.
Yeah. Okay.
Here. No, it's fine.
So maybe for the rest of you, you can turn over to the next page first. We'll look at calculus. The next. Okay.
Calculus. Wait a second.
Catalysis. Catalysis.
Oh,
okay?
catalyst. Catalyst.
Catalysis, okay? Not calculus, okay?
Oh my god.
Okay, so what we will look at next are some properties
Never
of
mind.
catalyst. Yeah, so we have
Did you get it?
catalysis.
No, because like I'm not running
So,
up like keep rolling.
yeah, so what is catalysis?
Different number.
So it is the use.
It's like I'm not with
Right.
this number.
Yeah, don't worry. Yeah, I really don't want this part to rule
I'm not
like industrial chem. Industrial chem is more than just this. It's a small part. You have 20 marks for each of the electives, and this will at most, that calculation will at most make up like a few marks of those 20 marks. Don't let that
Never mind.
like screw you, okay? Yeah, so we have other parts. So let's give our focus to the other parts now. Okay, don't worry, it's not the end of the world if you don't get that calculation. It's just a small part. So the use of a catalyst to speed up a reaction. We call this process catalysis. Okay, it's the process of you trying to make a reaction go faster by adding a catalyst. That's what this now means, catalysis. So the use of a catalysis to speed up a reaction. There are many unique properties of catalysts, which is why I gave you so much blank space in here on these two sides. Okay? So now I want you to look at the first one. Catalysts, they can speed up reaction by providing an alternative pathway, okay, with a lower activation energy. So for the first point, I want you to put down two types of reaction. One is the irreversible one.
Yep.
Yeah, so the irreversible reaction. The other is the reversible. Remember reversible reactions, sometimes we also call them equilibrium reactions. Because for reversible reactions, eventually, there will be a point when, let me test if you have done revision on equilibrium. What are two properties of a system at equilibrium? One is about the rate, one is about the concentration. What can you tell me about the rates of the forward and backward reaction at equilibrium?
I forgot it. Yeah.
They're equal. What can you say about the concentration? Remember, I
Different.
said
They're not equal.
They're constant. Should you say they become equal? Should you say the constant? Let me show you.
No, concentration isn't equal.
Concentration is not equal, but it's constant. Okay, it's
Okay.
what ages go.
Leo.
But we saw that here.
Not the test.
So I saw this here.
Not the same as the test.
So if I can find it in under 30 seconds, so should you. Okay, because we've gone through this together. So in equilibrium, these two features, you must remember, rates of forward and backward reaction are equal. But the concentration are not equal for reactant and product. They only remain constant. They only remain constant. If we are to show this in the form of a graph,
DJ.
this is the equilibrium state. Okay, yeah. So you have how many states of equilibrium here?
2,
3.
Oh wait, yeah, 3.
This is when the concentration remains constant. So this is the state of equilibrium. In the middle, you see another state, and finally you see a third state, right? 3 states of equilibrium. So,
Oh my God, that's
yeah, okay, we're back to here. Yeah, so irreversible reaction means A reacting to form B irreversibly. Reversible reaction, of course, means A can form B and B can form A, and at the end you will have a constant concentration of A and B. So can you draw a graph here? So for A becoming B, the reactant concentration of A, so if this is A and this is B, so A would eventually all be consumed. So it becomes 0. So this is the concentration of A. And for B, B would rise in concentration. So this is B. And for reversible reaction, both A and B will not fall to 0. Okay, it will not come to 0. So they will instead go to a constant point, reach a constant value, like something like this, for example. So none of these curves will fall to 0, because reversible reaction means eventually you reach an equilibrium, where the forward rate becomes equal to backward rate. Yeah. So can you put that under the first point? Yeah, all these are just for you to put under the first point. Okay. So catalyst speeds up reaction. So the first property. So catalyst speeds up reaction, so increases the rate of reaction. Yeah, for reversible reaction, it increases the forward and backward rate equally. Okay, so does it affect the amount of product formed then? No. Yeah, because when you add a catalyst, it will just make the forward and the backward reaction increase by the same amount. It will just make the forward and backward reaction rate increase by the same amount. So you really don't get more A or more B. Yeah, you will have the same amount of A and B. But can you tell me what would the graph be like if I add a catalyst? So this is reversible reaction without catalyst. What would a reversible reaction with catalyst look like?
Like double high. Yeah,
Should it be twice as high, or should it reach equilibrium faster?
reach equilibrium faster.
Yes, so if you really must draw it, okay, this is what it looks like. Let me accentuate it a bit more. Like it looks like this. But they will reach the same height, can you see? They will still reach the same height. It's just that they will reach equilibrium faster. Do you get it?
Yep.
Yes, okay, you still get the same amount of product. This is what I need you to draw in the first line.
Oh,
Just the
first
first
line.
line. Okay? So write down, because with the catalyst increases the rate of forward and backward reaction equally. So therefore, 2 outcomes. So number 1, the amount of product stays unchanged. So amount of product stays unchanged. But what is changed? Is the time it takes to get to equilibrium. Time to reach equilibrium is now shorter. This is the time to reach equilibrium. You see, here it took a while. Here it took much less time. Okay, so longer time to the yellow state. Okay, the yellow state is the state of equilibrium. Here you have shorter time to equilibrium. That's the only thing that has changed. Certainly not the amount of product. The amount of product is the same. Yeah. What about the irreversible reaction? I forgot to add. If you have space, can you add one more graph in my bed? So this is irreversible reaction without and with the catalyst. Okay. Can you tell me what would the graph be like if I add a catalyst?
Faster.
It will reach the highest point faster. But we don't use the word equilibrium here, so you will see something like this. It's kind of similar, you know. So like this. You just want the zero like much faster. Okay, so the rate would become zero faster. Do you remember the gradient, right? So this is the gradient. This is the gradient. This is the gradient. So you see it becomes zero faster. Okay? So the rate falls to zero faster. So that's the difference between irreversible and reversible reaction when it comes to adding or removing a catalyst. Okay? Yeah, so much for just this term, right? So, don't worry, it gets better. The second term provides an alternative pathway with a lower activation energy. So for your second bullet point there, can you help me draw two graphs? One is the Maxwell-Boltzmann distribution. The other, what are the axes labeled in? Sorry, yes. What about energy profile? Energy.
And reaction.
Reaction. Coordinate. Yes. Okay. So catalyst can provide. You don't have to copy this heading. So I'm just putting it down for you. But what you need to draw now is use the space wisely. Okay. So you use pretty much the same amount of space for the two graphs. And write down what these two graphs are called. This is the Maxwell-Boltzmann distribution. Yeah, I don't want to punish you to spell the word, just write SPD. The other is energy profile, but you must put down the label. When they ask you to draw an annotated diagram, don't just put two arrows there and walk away. No, you need to put down the units. Okay. So this is probability, or proportion, or number. Yeah, doesn't matter. You can write proportion. If you write the word number, just write number. Okay. So proportion or number of molecule with that Ke, and this is Ke. For energy profile, is energy and reaction coordinate. Okay? They both look kind of complicated, you see. But the Maxwell-Boltzmann distribution should be a lot easier. It is a single curve with two. Remember, this end must not touch. This end must not touch the x-axis. Okay, so I think I reminded you this yesterday. Okay, yeah, and this is the EA for when it is catalyzed. Where should I draw the EA uncatalyzed? To the left. To the left. And now you should shade some areas under curve. And you might want to take out a pen. Oh, in the exam, you should not shade the area like that, because you're just drawing dots. Instead, you should draw lines that go in opposite direction. For example, this goes in this direction, the other goes in the other. This is what you ought to draw. This is what you ought to draw. Okay, because you can't use color in the exam. Your answer color should all be written in black. Okay, so you should you can however point the lines in opposite direction to indicate that. Yeah, the area here. Yeah, okay. Is if you need to excuse yourself or bathroom, yeah, you can, yeah, okay. Because yeah.
So after this break, after energy.
Just a short break, okay. Yeah. So for energy profile, can you tell me how does adding catalyst affect the energy profile?
Decrease.
The EA will be lower than before, so you can draw this. Yeah, and then two humps. Okay. Usually there will be one more hump. But depending on the question, of course, if they tell you that the catalyzed reaction has 3 steps, then you draw 3 humps. Yeah, you can be flexible. Okay. So it almost sounds like they need to change seat every lesson. Okay. So this is the catalyzed reaction, and this is the uncatalyzed reaction. Remember, When you label the EA, should it be drawn from the left shoulder or from the right shoulder? Left shoulder, yeah, so show it. Yeah, yeah. And this one. Okay? Yeah, so this one. This is the EA uncatalyzed. Both of these are the EA catalyzed. They are both lower than the EA uncatalyzed. So it makes the reaction easier. Remember, the higher the EA, what will happen to the reaction? Is it the slower? Yeah, the higher the EA, the slower the reaction. This is why uncatalyzed reactions are always slower. Makes sense, right? Yeah, so this is why you need to add a catalyst. So that's point 2. What you need to draw in point 2. Okay? So you can lower EA. Next up, they are very specific in action. Oh, so for here, I want you to copy a few equations with the associated catalyst. Okay. So, yeah. You need a 1 minute break.
My brain can't
2
handle
minute
this
break. 2
anymore.
minute break. 2 minute break. Yeah, 2 minutes.
Oh my God.
Okay. You can go to the bathroom.
Yes, sir.
My brain hurts.
My phone.
Your what hurts?
Did you mix up the Maxwell from the capital in the left?
Oh, right. Yes, okay. The clarification. EA catalyzed should be on the left, my bad. Okay, typo.
Yeah, okay,
I don't
that
know what I'm writing. Okay, but you know what I mean. Okay, this is
What?
where the
You wanna
catalyst.
go up?
Yeah.
Go up
No.
and ask what's happening.
Well,
Mm.
they will have lesson. Have teacher have lesson.
So?
So,
Still so much noise. It's not a like excuse for
it's
this
not that. We have potential part of
potential crime. Tell us what happened. Why am I going?
Just to say something.
Yes.
Because when you teach when these things go on, you know like
You can check your calculation from the previous papers. You can also use this method on the graph on the left. Yeah, maybe you can try apply this. Try to apply this same method onto 2 data points in here. Just take any random 2. You should get a similar answer. Yeah, so you can apply this method onto this question. Pick any 2 random data points. Because in exam, I really can't control what they give you, right? What they show you in exam. Sometimes they give you like 4 sets of data. Well, in that case, you need to draw a graph. Sometimes they do you a favor. They show you just 2 sets of data. If you just see 2 sets of data like in this question, you use this equation directly. Use this method. So this is why I make this 2 separate methods. This method is more graphical. This method is more math.
What's wrong?
More linear,
Nothing.
math. What?
Teaching
Yeah, I told them already.
What? What is it?
I told them to fight.
Yeah. Not yet 5.
yeah, still does good.
They want to.
They were
Okay.
sitting in their seats though. I went.
So let's resume. Okay, so let's resume. Now, catalysts are specific. Okay, I want to check if you have all done revision on organic chem. How many reactions have we learned in organic chem that requires a catalyst?
So when
3,000.
Oh,
3 or 4.
2, 3.
maybe you can tell me what those equations are. Then we will know it better.
LIH.
Oh,
Yeah,
that's not a
they-
catalyst.
Oh no.
That's a reducing agent.
Metal.
Maybe I will start first. Okay. Like just like Ritika just mentioned, okay, is platinum. Yeah. What is that reaction that involves platinum?
Addition.
Alkene plus
Alkenes, alkenes.
hydrogen forming
Hydrogenation.
This is hydrogenation. Yes, hydrogenation.
Okay.
Write it down.
Who
You need to
invented
put
that
it.
name?
You need to
The
put
names
it.
are easy, the reaction is.
Third blank, please. Okay, third blank. Don't take up all the space. We have a lot to write here. For this part, make your like a word really small. So this reaction right now is called hydrogenation. So mark it here. Third blank. So hydrogenation. The second reaction is, maybe I'll give you some hints. It's a reaction that requires consulfuric acid,
What is that?
and it's reversible, and it involves two reactants.
Alcohol to alkene. Is it?
No,
no,
that's
no.
dehydration.
To aldehyde. To
No.
acid.
No. It's alcohol to something.
It's something plus something forms something plus something.
What do you mean? What is the meaningless thing?
It's alcohol plus carboxylic acid.
To ester.
Yes.
Ah.
Oh, the measure is back. Okay. So
No,
it's
not really.
Yeah, ester and
And water.
let's see if I can find
Water.
Yeah, okay, yeah, and water. Where did you mention that? Well, I remember there was a map.
I don't care about the map.
Yeah.
I printed it out. I only remember the
Where
MTR.
did the map go?
Yeah, I just remember the MTR one. Yeah. Along the lines. Next station. That
Here.
one.
Yeah, so you see alcohol and carboxylic acid, or you see catalyst.
Wait, that's reversible?
This is reversible.
Yeah.
This is reversible. But because I can't show the reversible nature here, I didn't draw it here. But it is reversible. Did I mention that? Oh, I think I did. So this is consulfuric acid used in this reversible reaction. Okay? So write down the name. If you don't remember that now, try to remember that back then, remember that now. Write down esterification.
You printed it? Yeah.
Cation, yeah. So you have water and ester on the right. The catalyst is consulfuric acid. But this is not a transition metal catalyst, but nonetheless it's a catalyst. Okay? We have also the making of ammonia. What is needed to make ammonia?
Nitrogen.
Nitrogen and
Hydrogen.
hydrogen. Yes. Okay. Does anyone remember the catalyst? Yes, Haber process. What is the
AL2O3.
what is the catalyst? It's
Oh,
iron.
yeah,
Yes,
yeah.
a finely divided iron powder.
400 degrees
Yes, 450 degrees
Whoa,
C.
you remember that?
and 200 ATM.
200 atm. Okay, yeah, so
Yeah,
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 200
yeah.
atm. That's the conditions. Okay, so write down the condition, please. The name
What's
is
that
yes,
finely
Haber
what?
process.
Finally
And the
divided.
condition, yeah, is 400 degrees
Very,
C
very,
and
very
200
small,
atm.
powder.
Okay, and one more, okay, well, two more, okay, so two
Just
more.
one
We
more.
have-
How many more?
Actually, there are a lot more, but I don't want to, scare you. Okay, what about catalytic converter? Yes, what is the reaction?
Also platinum.
Platinum, yes, okay.
Wow.
This is the catalytic converter right now. What is the reaction?
Uh,
What plus what gives what plus what?
Carbon
Carbon
monoxide
monoxide.
plus nitrogen monoxide.
Yes, forms two harmless substances.
Carbon
Carbon
dioxide.
dioxide and
Nitrogen.
Just nitrogen, not NO2. NO2 is
NO2
also
is
a
toxic.
Okay, it's toxic, yes. Okay, so 2221. 2221. Okay, so catalytic converter. Yeah, so that's this one. One more.
Oh no.
It's
What
the
more?
contact process. Contact process, okay, which makes sulfur trioxide. So you have contact process where sulfur dioxide and oxygen combines to form sulfur trioxide. Can anyone name this catalyst?
Vanadium.
Name.
No.
Vanadium.
Vanadium
Vanadium.
5
Dioxide.
Tri-
Dioxide.
tetra.
Just vanadium
Pentoxide.
dioxide. When do you call it something pentoxide? It's when you have, yeah, write this down. N2O5 will be dinitrogen pentoxide. Pentoxide. Yeah, this is covalent. You will only need to indicate how many there is when it is a covalent compound. But what about vanadium 5 oxide? Is it a covalent compound?
No.
No, because it has a metal, it has a non-metal, it is an ionic compound. So how do we call this then? We would just call it vanadium 5 oxide. So I know the formula look very similar, but their names can't be any more different. So this is vanadium. What does the number 5 mean?
Oxidation
number of which element?
vanadium.
Vanadium, yes, okay. So you may want to highlight this. And write down, this is the oxidation number of vanadium. You can find that by plugging -2 into O. Remember the oxidation number of each O is -2, right? So 5O would give -10. So, and what must each V be worth if they add up to 0? Plus 5. Plus 5. Okay? So that's vanadium dioxide. So you see, many, if not all, of the catalysts, what do they have in common? Do you see a transition metal there?
Yes.
Yeah, Fe is transition metal, Pt is transition metal, okay? V is also a transition metal. This is what I wrote in here. Many catalysts catalyze a different reaction, and they are often what? You can see the 4th point on the same page. They are often elements. So write an example under element. So these two are, these three are elements. They are either elements, compounds. So this is a compound, or they can be ions. Well, actually, there's one that we mentioned not long ago. Do you remember the I minus plus S2O2 minus that one?
Yep.
This one, this equation. What is the catalyst in here? Fe3 plus. So this is our last example, ion. So they can be ions. So put that Eg under ion and write Fe3 plus. Under compound, write V2O5. Under element, write down Pt and Fe. Okay? So there are no lack of examples of catalysts. Okay, done on this page. Let's turn over to the next
One
one.
page.
Done on this page.
On this page.
Okay, so next, well, catalyst works better in powdered form. Okay, so if you want to experiment or experience this firsthand, you can grab some hydrogen peroxide from the pharmacy and remember the peg liver. Have you tried adding peg liver into hydrogen peroxide? No. Yes. Yeah, it contains the
What about
enzyme caspase. But
calcium?
because you don't have access to this chemical catalyst that we'll be using, you can use peg liver. When you put peg liver into hydrogen peroxide, it froths.
Yeah.
Why?
Yeah.
Do you know that it will froth? No. Maybe you can try that when you have free time. Okay. So this is which point is this? The 5th point. Okay. So catalyst.
What is the point?
There are 4 points on the previous page. I discussed these 2 points together.
Oh, yeah.
Yeah. Okay. So the 5th point now. Catalyst works better in powdered form. Okay. So in powdered form. So below, I want you to draw 3 different. First, write down this equation. H2O2 becomes H2O and O2. This is the other reaction that you should know, which I didn't put on the previous page as I don't have space there. It's MnO2. Can anyone name MnO2? Like how you name V2O5?
Manganese.
You must not use dioxide. This is not a covalent compound. So, manganese, can you find the oxidation number of manganese?
2 plus.
It's not 2 plus.
Wait, no.
O is -2 each. There are 2 O.
Four.
So what is the final
Or
answer?
manganese 4 oxide.
Manganese 4 oxide. Write this down. Yeah, so manganese 4. Remember, you must not say dioxide.
Yeah.
This is not like carbon dioxide, sulfur dioxide. Those things, you can name them in dioxide because they are covalent. This is not covalent. So manganese 4 oxide. It is a black powder. Peach black. Okay, so this is a black powder. Okay, so you can add it into the hydrogen peroxide with a spatula. Don't say spoon. We don't use spoon in chemistry. Okay, we use a spatula. Okay, so now can you draw 3 conical flasks on the right? Don't use up all the space yet. Okay, I want you to include yet another graph on the right. So this is what you need to draw horizontally in this part. What's in powder form?
What is it?
On the top. So draw these things on the first plane. We have 3 experiments here. Okay, so experiment 1, experiment 2, and experiment 3. All these experiments have one thing in common. They have the same volume of hydrogen peroxide. But what's different? To the first one, there is no catalyst added. No catalyst. To the second one, there is a lump of MnO2 added. Underline the word lump. A big block. Okay, so of manganese 4 oxide added. To the third chemical class, you did not add a lump. You add powdered manganese manganese 4 oxide added. And note that the manganese 4 oxide added should be of the same mass. This is for control experiment. Okay, you know you can't add more catalyst to one than the other, just to keep things fair. Now, what I need to do now is to show me the volume time graph. If I connect this to the syringe, if I connect this end to the syringe, yeah. So what would the volume of oxygen collector be like? So this is the volume of oxygen collector. We are collecting oxygen, using syringe. So can you show me the results of experiment 1, 2, and 3? Yeah, what are they like? So let me use a different color pen. Yellow pen for experiment 1. For you can use different types of line, dotted line or solid line, things like that.
Slime though, very slime.
I really
So,
It's very difficult to learn.
right, any idea which? Which one, do they end up at the same point or different point first?
Same point.
Same point, why is that?
It's not like
Is it very
the
common? But you're
volume
right.
should be the same.
Because
It's
how
not-
much oxygen get formed depends on what?
The amount of reaction.
How much reactant there? Did I change the amount of reactant?
No.
No. So therefore, can you draw this there? And maybe let's look at the first part first before we can draw the graph. Because I can't draw the graph without showing you also the first part, which is what I want to ask you next. Which should be the steepest?
Last one.
Yeah, the last one. Why? Well, not only because it has a catalyst added, but because powdering these catalysts means you are increasing the what?
Surface area.
Surface area. Okay, so therefore, can you put down if you still have space, you can write down the catalyst and the surface area. Okay, yeah, we'll look at the catalyst and the surface area of the things in this experiment. Okay, experiment 1, 2, and 3. So with the catalyst, with the first one, there's no catalyst. Yeah, the second one and the third one, they both have a catalyst. But in terms of surface area, okay, there's no, this is just not applicable with the first one because we don't even have a catalyst. But for the second one, the surface area is small. But when you use powdered catalyst, the surface area is large. So that means you have two favorable factors, both the addition of catalyst and the inclusion of high surface area, right? Large surface area. So this is why moment of truth, okay? You have the yellow curve, the orange curve, and the green curve should be found here. Is that clear? Do you all understand why it should end at the same point now? Yes, okay. If you are still not fully convinced, you can write down. This is because the amount of O2 formed depends on the amount of H2O2 present, which I control in all three experiments. So depends on the amount of H2O2 present, which is fixed. Yeah, so which is fixed? This one. Okay? Yeah, so that's what you need to draw in here. And the second last point is the most annoying one. Okay? Yeah, there are two types of catalysts. Yeah, there are two types of catalysts. We have homogeneous catalyst, this is not the first time you hear this. We have homogeneous,
What is that?
we have heterogeneous. Okay, when did we first introduce this term? Equilibrium. Yeah, remember an equilibrium with everything in the same state, like gas. What do you call those equilibrium?
Homogeneous.
Homogeneous. For equilibrium, like maybe take a look at this one. N2 gas plus 3H2 gas forming 2NH3 gas, they are all gas. So it's homogeneous equilibrium, that's it. A heterogeneous equilibrium will look something like this. You will see things of different states. So solid, gas. This is heterogeneous equilibrium. Now, we will also use the same terms to describe catalysts. There is homogeneous catalyst and heterogeneous catalyst, okay? So you can write down types of catalysts, okay? So they can be homogeneous or heterogeneous. Don't worry, very often they will not ask you to spell this word, but at least make sure you know what it means, okay? I know this word may be difficult to spell, but just try to understand the meaning, that's more important. So homogeneous catalysts are in the same phase or state as the reactant. Let me show you an example. Yeah, this equation you may find it boring already. Is I minus plus S2OA2 minus becoming I2 plus 2SO42 minus. The catalyst is in the same state or phase as the reactant. So can you see AQ, 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 AQ? Everything is in the same state. So therefore there is not a new thing you need to learn here. It's the same definition you learn in equilibrium. Homo means same, hetero means different. Okay, so catalyst means same phase as reactant. And I think you guess it. Heterogeneous, of course, will be catalysts that are in different state than the reactant. Yeah, what are some examples? Well, there are a lot more examples of this type. Look at the Haber process. What is the catalyst of Haber process? Fe. Solid. What are the states of the reactants? Gas. Okay, so you have N2, 3H2 plus becoming 2NH3. You have gas, but yet the catalyst Fe is a solid. So therefore, like on second thought, you see this is actually not very complicated. Okay, it's just like what you learned in equilibrium. Just that we have catalysts sometimes in the same phase as the reactant. Sometimes they are in different states than the reactant. So, how do catalysts work? And why is it that catalysts will not be, you see this key point here, it will be chemically unchanged. Why can catalysts remain chemically unchanged at the end of the reaction? Because they can be regenerated. So do you remember this equation again? It's 2I minus plus 2Fe3 plus. What do you call things that are formed in the middle of a reaction but then will be consumed immediately? So you see it's the same stuff over and over in this chapter. So you have I2 and the S2OA2 minus can then react with your intermediate to form back your catalyst. So because the catalyst come and go, okay, this is why we say it is regenerated. So therefore the first term, underline this term. Catalyst can be regenerated or reformed, okay? Yeah, so a catalyst is regenerated. This is the first way in which catalysts work. The second way in which a catalyst will work is slightly more complicated, just slightly, okay, just slightly.
Slightly.
So, yes, slightly. So on the right, I want you to draw a like a trapezium, okay, like this. So this is iron. How do heterogeneous catalysts work? They provide a surface. They provide a platform for the reactants to come. Okay, so does anyone know what the bond is that hold two N atoms together? Is it a single bond, double bond, or triple bond?
Triple.
Triple, yes, okay, and you should know very clearly why that's the case. Because hydrogen has only how many electrons in the outermost shell?
One.
One, and it is unstable. Nitrogen, in its unbonded state, knowing its atomic number to be 7, what is the number of outermost shell electrons? If nitrogen has 7 electrons in total, how many electrons must there be in the outermost shell? 5. So let's draw 1, 2, 3, 4, 5. Does that make nitrogen stable?
No.
No, because 5 is not octet, nor is it a duplet, okay? Now, what can two nitrogen do to help each other become stable? They can bond. How many electrons should they deposit in between them to make each of them stable? 3 each. So you have dot, cross, dot, cross, dot, cross. How many left on each nitrogen? 2. And when you check again, can you see that in here? This is only 5. So this is why I drew unhappy phase. Unhappy phase means unstable. Yeah, and on the right, after they bond, you know when you share something with others, what you share belongs to both of you. Okay, so when you check this circle, how many electrons are there? 8. So both are stable. So this is
Where is the one
Yes.
yeah, okay. Yeah, oh, that's just error there. Okay. So what about for hydrogen? What is the bond?
2.
Just
Single bond.
1.
Oh.
Because if you are hydrogen, you have only 1 electron. That's the most you can give. Okay, and that automatically makes them stable. Because hydrogen doesn't have to have 8 electrons for it to be
It's
happy.
2.
It only needs 2, right? Yeah. So this is why the nitrogen bond should be a triple bond. And the hydrogen bond, so I'm showing you how you can go from just knowing the electron arrangement to knowing what the bond is that hold the atoms together. Yeah, and what do you see? Does this bond look like a weak bond?
No.
No. That means this reaction, just like this one. Do you remember why this reaction has high EA? Because
They're both anions.
so do
They
they
repel
attract?
each
They
other.
repel. Yeah. You should tell me that they repel. Okay. So they're slow.
They-
When asked, why would this reaction have high EA? You know, because the light charged ions repel. Okay. Next, what about this reaction? They will suddenly ask you, explain why this reaction is slow. Now you say,
Strong,
because the bonds are strong, too strong to be broken, right? Yeah, so same thing. So you jump on this time, this is important, okay? This is the type of question they like to ask
For how
you.
many strong?
So write down, why is this slow? Or in other words, why does this reaction have high EA there? This time you can't refer to the charge, they are both neutral. This is because N triple bond and H single bond are both strong. I know you would disagree. You would say, wait, I understand why N is triple bond is strong, right? But why is H single bond strong then? Yeah, why, right? That's because H is small. When two atoms are small, the bonds that is formed between them would be stronger than you can form between two larger atoms. And for those of you who do physics, you will know why. Can you see? In which case are the oppositely charged things closer to one another?
First.
Is it when the atoms are both small or when the atoms are both large?
Small.
Small. This is why HH bond is strong, because the atoms, they can come pretty close to one another. But don't worry, this is not very important, but when you read the book, you may be really puzzled, okay, as to why is HH bond strong? Well, that's because H is small, okay? Yeah, don't worry about that. This is not as important in the DSC. But now, look at the Fe. When the nitrogen triple bond and the hydrogen single bond come over, they will be stuck on the catalyst in a process. So write down the name. This is a keyword. We call this adsorption. I know what I'm writing. This is not a typo. This is not a spelling error. It's adsorption. In biology, you may have heard of absorption. What does absorption mean? Absorption means go into. Adsorption means stick onto. Just stick onto. Okay, it did not go inside the catalyst. It just
Oh my
attached
God.
loosely.
Learning new English word.
Yes.
English lesson.
Oh, this is not a common English word, okay? So
Like
don't worry.
chemistry
if
is
you
combined
don't know
between
this.
math and English.
Okay, so can you put down adsorption means stick onto. Okay, this is not to be confused with absorption. So absorb means goes into something. This is a real word,
No.
okay? Like an actual English word, okay? So adsorb means sticks onto. Oh, okay, yeah. So and they are not the same. And I know what I'm writing is adsorb. with D. Okay, so adsorption of reactant. So when reactants become adsorbed, the bonds are broken. Okay, so you now have an N, just like like those flowers. Okay, like they attach onto this green lawn here. So the nitrogen and nitrogen they become attached temporarily. The hydrogen they are also attached temporarily onto the surface of the catalyst. Then what will happen to them? The reaction will happen between these atoms. So free hydrogen would go to one nitrogen. The other free hydrogen would go to the nitrogen here. So we say a reaction then occurs. And what do you think is the opposite term to adsorption? Desorption. Desorption. Okay? Yeah, so the next and the last stage is that, once the NH3 successfully forms, so you see here, a nitrogen atom is successfully connected to free hydrogen.
I know.
They would then
Now I know why
leave.
something to chemistry.
Yeah, so they will then leave. And this one is just as easy to remember. Desorption. You have adsorption with a D. You have desorption with a D as well. And can you tell me what happens when they go? When they go, what would they leave behind? A free surface of iron. This iron, is it available again?
Yes.
Yes, it is available again for another round of reaction. So this is what I meant here. It is either regenerated, like we saw on the left. So a catalyst can either be regenerated, it is actually reformed, or the surface is available again. Available again. So and this surface can go back into here. And now for those of you who do biology, you may find this familiar. Do you remember learning about enzymes?
Yes.
Yeah, enzymes, they have an active site. When they find the substrate, they will, like like this Pac-Man, there will be a reaction. They will then turn this reactant into products and they let go. Yeah, and the Pac-Man is available again, right? You see? So this just goes on and on. And this should be especially familiar to those of you who do biology.
Yes.
So enzymes are biological catalysts, which is what we come to next. Okay?
Oh, no.
So we are not done with this.
Not
okay?
yet.
The
You're
last
not
one,
done yet.
last one on this page. Catalysts can be poison. Okay? Do you remember learning about a concept called a thing called lead petrol? What is lead petrol?
Lead petrol.
Lead petrol.
Oh, lead petrol. Yeah.
Lead
yeah.
petrol means petrol with lead added
Yeah.
to it.
Yeah.
Is it because the manufacturer wants to poison you?
Yes.
No. They add lead into petrol to make it burn more smoothly. Okay, but unfortunately, some of the lead particles they will escape in the exhaust pipe, in the exhaust gas, and when you inhale it, if you if you're breathing it in for too long, it will affect the nervous system. So they may be, put on this term, poisoned by impurities such as lead in lead petrol. So this is, there's only one example that you need to know. Okay, so just know this specific example. It is the use of catalytic converter. Do you remember that aspirin must not be taken with alcohol? So here we have a similar thing. Lead petrol cannot be used with catalytic converter. Okay? Okay, let me finish this very quickly. So this is the engine. So this is the engine, and then this is the catalytic converter. The catalytic converter. Remember, the catalytic converter provides an adsorption surface, so it has platinum on it. So the carbon monoxide and the nitrogen monoxide, they can combine to form, what are the two products?
Carbon dioxide and nitrogen.
Yeah, nitrogen. Okay, so the carbon dioxide, so they can form because, so the carbon dioxide, so first we have adsorption, then we have desorption. Okay, so this is like, there's nothing wrong with this thing here. But then when you use lead petrol, okay, let me finish this real quick. when you use lead petrol, lead would cover the surface. So this is lead. So would the carbon monoxide and nitrogen monoxide be able to absorb themselves anymore? No. Okay, so you see, no absorption can occur. So therefore, you are making the catalytic converter not functioning. Okay, it's not functional anymore. So just write down one thing. Lead can poison the PT catalyst by coating it. Okay, yeah, this prevents adsorption. So, and by stopping adsorption, you stop the reaction. So the catalyst is not functional anymore. So this prevents, and remember you spell the word correctly. So adsorption of reactant. So the
So lead is not the substance that poisons.
lead is a substance that poisons the catalyst.
Yeah.
Lead can poison the catalyst. The catalyst is platinum. So lead coats itself onto the catalyst. Yeah, it's like it's blocking the way of the carbon monoxide and nitrogen monoxide. Okay? Yeah. So we'll end this here. Okay? So yeah, if you have a question, you can come. So the catalyst will not work anymore. So you need to replace it. So need replacement. So is that clear? So that concludes this part. So we'll carry on with the biological catalyst next time. Okay?
So like we coat the platinum with lead.
Yeah.
If we do that, yeah, let it coat